Okay, hey, this is Mrs. Cribb. I'm going to lecture through the notes that would have been covered in class for those of you who are missing the in-class instruction, and you can watch this. So pull out your notes. We're going to be in Chapter 12C, so you can pause it and do that and then come right back. A colligative property is a physical property of a solution that depends only on the number of particles without regard to type. That means it just doesn't matter what they are. All we are is counting the number of pieces they break into. And it affects the boiling point, the freezing point, and the vapor pressure and osmotic pressure. We're going to focus on boiling point and freezing point, but I do want you to know a little bit about vapor pressure. Vapor pressure depression. At the surface of the solution, the solute particles fill positions that are normally occupied if the solute is less likely to become a gas or less volatile. Volatile means how likely is it to become a gas. So likely to become a gas. Then the vapor pressure will be lowered. Now you can look in your textbook at figure 12-13. A mole of sodium chloride added to a liter of water will lower the vapor pressure more than adding a mole of sugar, because sodium chloride breaks into sodium ions and chlorine ions. So it breaks into two pieces. Now then we look at aluminum chloride. It will lower the vapor pressure even more than sodium because it breaks it into one aluminum ion with a +3 charge and 3 chlorine ions. All right, I have a couple of pictures down here of what I'm talking about. Sugar, and if you watch that video with Tyler DeWitt, this is a sugar molecule right here. Sugar breaks apart into molecules, and the crystal itself breaks apart into individual molecules. And so we're going to talk about in a few minutes about this little thing called I. I is representing particle count, and you could also think about it as molecule count, but we're just talking about how many pieces. So in this case, since sugar just breaks apart into one molecule, its I value, its particle count, would be 1. Sodium chloride breaks apart into the chlorine and the sodium pieces. So sodium chloride breaks apart into 2 spots, so its I value equals 2. This looks like angry sodium for some reason. So aluminum chloride breaks apart into 3. Now I couldn't find a really great picture for this, so this is the aluminum chloride molecule or compound. It's going to break apart into aluminum and then 3 of the chlorines flying around out here somewhere. So that means it breaks apart into 4 pieces. So for aluminum chloride, its particle count would be a 4. All right, that's going to be very important for what we're about to do. Okay, before I go into boiling point elevation, let's talk again about this vapor pressure thing. Let's draw a picture. We have a container, and inside this container I have water. Oops, it's still green. I wanted blue. There we go, water. So we have a whole bunch of water molecules in here, because that's what the solvent is. It's water. So I'm going to draw a lot more blue water molecules. Okay, now if I dissolve something like sodium chloride in it, I'm going to make that red. Then you'll have the sodium chloride ions floating around in the water too, and since it's the solute, it's going to be less of it, but some of it's going to be sitting up here on the top. Now this helps lower the vapor pressure because there's intermolecular forces between the water and the chlorine and sodium, kind of holding them together, keeping them from escaping, right? Now, because it's sitting up here on this top, it's also taking some of the spots that the water might want to escape. Because normally, if the water molecules get enough kinetic energy, they escape and become the vapor pressure, the vapor. And remember that vapor pressure is pushing down. And vapor pressure is pushing up, rather, and atmospheric pressure is pushing down. Got those. There we go. Fix that. Okay. Atmospheric pressure is pushing down, and vapor pressure is pushing up. In order for things to boil, the vapor pressure and the atmospheric pressure have to equal each other. That's what boiling is. That's what we said in the last chapter. So if it takes more heat to make more water vapor, because all these particles are sitting here in that spot and they're kind of holding the water, they're helping to hold the water in, then that means that the vapor pressure is going to be also lowered because boiling temperature is raised. The higher if the normal boiling point will have a certain vapor pressure, and if the vapor pressure is lowered, you have to increase the boiling point to get the vapor pressure strong enough to equal the atmospheric pressure. So what does that mean? That means if the more pieces that these molecules break into, the more spots they'll fill. So I could have some sodium chloride and some or some aluminum chloride. The more spots they fill, the lower the vapor pressure will be, the harder it will be to boil it, the higher the temperature has to get before it boils. So when there's a high boiling point, it means that the vapor pressure was lowered at the regular boiling point. Okay? All right, let's talk about the formulas we're going to need. Now we're going to use formulas to calculate how much does our boiling point go up. Solute particles lower the vapor pressure, that's what I just said, and thus raise the boiling point. So the formula we're going to use is delta T sub B equals I, which is that particle count right up here, K sub B, and then little m. All right, the K sub B is this molal boiling point constant, and you'll just be able to look that up in a chart or it'll be given to you. And then the little m is molality. Okay, so the I has to do with the solute. So like for instance, sodium chloride would be my solute here. It breaks into 2 pieces, so my I is 2. Aluminum chloride would be my solute here. It breaks into 4 pieces, so my I is 4. And sugar could be my solute here. It breaks into 1 piece, so my I is 1. With covalent molecules, the I is going to always be 1 because they're not going to break into ions. All right, this K sub B has to deal with the solvent. So it's the molar boiling point constant of the solvent, and the M is the molality, and that has to do with the whole solution. So that way you'll be actually putting all these things into this formula. Another formula you're going to need is the delta T sub B is equal to T2 minus T1, or you could say T final minus T initial. All right, we're going to use these formulas now. Okay, now we're going to do example problem 12.8 from the textbook, which is found on page 314. And I want to make sure that you understand we're going to be using my formulas and not the ones from the textbook, because they don't have an I in theirs. They use something called particle molality in their M, and I don't want to do that just because it tends to confuse students more. So this is the question. We have what is the boiling point of acetone? So that it's asking for its boiling point when 0.500 moles of naphthalene, and they give the formula for naphthalene, which is C10H8, is added to 1 kilogram of acetone. And then it gives me the molal boiling point constant, the K sub B, is equal to 1.71 degrees C per molal. First of all, since this is being dissolved in acetone, this is the solvent, and this is the solute. Keep that in mind. Let's write down our formulas. Delta T sub B, the change in the boiling point, because delta means change in, is equal to I, the particle count, K sub B for the solvent, molality. Okay, what is the I? Well, naphthalene, notice carbon and hydrogen are nonmetals, so 2 nonmetals makes it covalent. So the I is equal to 1. It breaks down just into molecules. So 1. So for all the covalent molecules, you're going to use I as 1. The K sub B is 1.71 degrees C per molal. And now I've got to figure out what the M is. I've got to the molality into this spot. And so I've got to calculate that. The molality is moles of solute over kilograms of solvent. All right, the moles of the solute they gave me this time right here. So I'm going to put that in there, 0.500 moles. And the kilograms of solvent is 1. So this is just a 0.500 molal solution. So that's what I'm going to put here, 0.500 molal. Cancel out my M's and do the math, and I'll be able to get my change in the temperature, which is 0.855 degrees Celsius. 3 significant figures, 1, 2, 3, because of this, 1, 2, 3. You're not going to use the K sub B for your sig figs or the I. The I is going to have infinite significance. Remember, if you can count something, it has infinite significance. So you're going to use this value right here, and this one is a definition. Okay, we're going to go on from here now. Something important to remember, ionic compounds break apart into ions, and I've been talking to you about this. You will need to multiply the number of moles or particles by the number of released ions. The result is the particle molality. The textbook talks about particle molality, where they incorporate the particles count into the little m, and we just use the I to separate it out to make sure that we're accounting for it. Sodium chloride would be 2 because of the sodium ion and the 1 chlorine ion. ACl would be 4 because we get 1 aluminum and 3 chlorine ions. And covalent molecules do not break apart, so you get 1. Okay, let's do example 12. Oh, wait a minute, it was chlorine. I didn't finish writing chlorine now. All right, example 12.9. This time we're going to have 425 grams of magnesium chloride, and you'll have to figure that out. Magnesium, Mg, has a +2 charge. Chlorine has a -1 charge. You get this from either looking at the periodic chart and seeing that magnesium is in column 2, and everything in column 2 has a +2 charge, or you can look at your oxidation chart, which they're under resources, so you'll need to print one out. Crisscross, so that magnesium chloride has this formula. So we have 425 grams of magnesium chloride added to 675 grams of water. And the question is asking me, what is the boiling point of this solution? All right, first job is to figure out which one is the solvent and which one's the solute. Well, magnesium chloride is the solute because there's less magnesium chloride than water. So this is the solute. That makes this the solvent. So the solute I'm going to have to turn into moles, and the solvent I'm going to have to turn into kilograms. And the solute's where I'm going to get my I. So I for the solute is magnesium chloride. That's going to be 1 magnesium atom and 2 chlorine atoms. So 1 + 2 is 3. So the I value is going to be 3 because magnesium is a metal. So metal, nonmetal, ionic. It breaks into 3 pieces. All right, so now I can use this information to calculate. So delta T sub B, the change in the boiling point, is equal to I K sub B little m. All right, and I is 3. The K sub B for water you will have to look up, and it is 0.512 degrees Celsius per molal. Like I said, that'll be on a chart, and then we have to calculate the molality then. All right, and what is molality? That's moles of solute per kilogram. Per which kilogram? There we go. Per kilogram of solvent. All right. I've already configured the solvent out. I take the 675 grams and turn it into kilograms by dividing by 1, 2, 3, by dividing by 1,000. So the kilograms of solvent is 0.675 kilograms. Okay, because I just told you right there, there's the solvent. Okay, now we just got to figure out how to get 425 grams and turn it into moles. So obviously I'm going to need the molar mass. So magnesium and chlorine. Chlorine 2 times 35.45, and magnesium is 1 times, okay, you'll have to look in the back of your periodic chart to get the molar mass of magnesium. It's 24.31. Whoops. 4.31. Okay, now let's pull this up and add that together. Whoops. There we go. Wrong button. There we go. 24.31 plus 2 times 35.45. And that's 95.21. That is the molar mass. 95.21 grams. All right, now that I know the molar mass, I can convert my mass that they gave me, which is 425 grams, into moles. So 425 grams of magnesium chloride. 1 mole of magnesium chloride we just determined weighs 95.21 grams. So we have to change the amount we were given into how many moles that would be. So I'll pull my calculator right back up. And we have 425 divided by 95.21. And that is 4.46. Now it's 3 significant figures because 425 has 3 significant figures. So 4.46 moles. Okay, that's how many I have. And this right here goes in this spot here. 4.46 moles. Now I can calculate the molality. 4.46 divided by 0.675. And that is 6.61. 3 significant figures again. 6.61 little m. Okay, that's what I got to put over here now. Now the little m's will cancel. And I'm going to do my math on this part and figure out what the change in the boiling point is. So 3 times 0.512 times 6.61, and that's 10.2, because 10.15, but again, 3 significant figures, so 10.2 degrees Celsius. That is the change in the boiling point. But this question is not asking me for the change. They actually want the new boiling point, so we're going to calculate the new boiling point. So we have to use that second formula that we had before. Delta T sub B is equal to the second temperature minus the first temperature. And here we're talking about boiling points. So the final boiling point minus the original boiling point. You could do T final minus T initial, or you could do T final minus the original. Anyone that makes you realize that you're dealing with the final boiling point because of the change and subtracting out what the original boiling point was. So this value here is the change. So I got to put it in this spot. 10.2 degrees Celsius equals the final boiling point minus the initial. Well, what is the initial boiling point of water? It's 100 degrees Celsius. And this is going to be a standard, so you're not going to worry about your sig figs on this one. Now, you should know that water boils 100 degrees Celsius. I won't give you that information, but I will give you the boiling points of other liquids if you need it in the question. So now just add 100 to both sides, so that the new boiling point is 110.2 degrees Celsius. So notice that the boiling point got hotter, and that's what you expect. The boiling point should go up, and the freezing or melting point should go down. You should increase the time when it's a liquid. That's what happens here. You increase the time that it's a liquid. All right, if you need to stop and pause periodically and write stuff down, please do. We're going to go on now to 1210. What is the molality of a solution of sodium chloride? So we have sodium chloride, and it wants to know the little m. And we have a solution of it, so it's dissolved in water. It says in water, if the solution has a change in the boiling point of 0.400 degrees Celsius. This one is actually pretty easy. Write down the formula that you have. Always, in these things, you write down your formulas and see what you can fill in. And then that, a lot of times, leads you right to what you need to do. Here's the change in the boiling point. Okay, what is I? That particle count, the number of pieces that sodium chloride breaks into. And sodium chloride breaks into 2 pieces, sodium and chlorine. So the I is equal to 2. All right, the K sub B is the molal boiling point constant for water again, which you'll get from a chart or directly in the question, depending on how it's put. And then, so the only thing you're missing is the molality, and that's what the question is asking for, the molality. So this is just a simple plug and chug kind of deal. All right, so divide this by this, and you'll end up with molality equals 0.391. If you aren't able to get that problem, it is probably because when you divided, notice the C's cancel, that you divided by 2 and then you multiplied by the 0.5. Make sure you're dividing by all of this quantity. All right, freezing point depression is, remember I told you the boiling point goes up and the freezing point goes down. Freezing point depression formula is a little bit different than the book as well, so you must use this one. Negative delta T sub F equals I K sub F M. The molal freezing point constant is K sub F. It's just like the boiling point one. You'll look this up on a chart. And then the second formula is very similar to the boiling point one. The change in the freezing point is going to equal to T2 minus T1, or T final minus T initial, or T final minus the original one. All right, and there'll be a chart where you can find all the values that you need in your textbook again. This time it's on page 316. So let's do example problem 1211 from page 316. How much will the freezing point of phenol, okay, we have phenol, change if we have 4 moles of naphthalene? It just says the word naphthalene are dissolved in 2 kilograms of phenol. And then it tells you that naphthalene is covalent and thus contributes 1 mole of particles. So naphthalene is covalent. Naphthalene is the solute because it's being dissolved. They give you the moles, and since it's a solute and it's covalent, the I is 1. So this is the solvent. So all we have to do is put stuff in here and figure out how it's going to change. So negative delta T sub F. Oh, let's rewrite that one. Negative delta T sub F, there we go, equals I K sub F M. The I is 1. The K sub F is one of those things you got to look up for phenol, and it is, let me find it, there it is, 7.40 is the constant. 7.40 degrees Celsius per molality. And then I'm going to have to calculate the molality, so I'm going to do that over here. Molality is going to be moles of solute per kilogram of solvent. So the moles of the solute is 4 moles, and the kilograms of solvent is 2. So that's just an easy 2.00 molal. Okay, so put that over here. 2.00 molal. Cancel your M's, do your math, and you're going to get that the negative delta T sub F is equal to 14.8 degrees C. Okay, then the textbook says that just the change in the temperature is 14.8, but the temperature change is going down. So in order to incorporate the fact that we know it's going down, we divide by the negative sign, so we get a negative 14.8 degrees Celsius. So what is the change in the temperature? It's a negative 14 degrees. So what will the new temperature be? And I don't know that they ask you that in the textbook, but I want to ask you. So what's the new new freezing point? All right, we use the second formula. Delta T sub F equals T2 minus T1. All right, now I know the delta T sub F, and this is why I use the negative sign, because it will work perfectly to incorporate into this formula. Negative 14.8 degrees Celsius is equal to, I would need to know what's the original boiling point of the solvent, which is phenol. Okay, I don't know that off the top of my head. So I look on the chart on page 316 and I find it. The normal, freezing point phenol is 40.9. Freezing point is what I was talking about. So 40.9 degrees Celsius is the normal freezing point. So add it to both sides. And the new freezing point then is going to be 14.8 plus 40.9, or negative 14.8. So negative 14.8 plus 40.9, and I get 26.1 degrees. So the new freezing point is 26.1 degrees Celsius. Notice the freezing point is lower than the original freezing point. So I was dealing with the freezing point here, not the boiling point. Just making sure we keep that straight. All right, the more ions or particles the solute breaks down into, the lower the freezing point will be. Calcium chloride lowers the freezing point more than sodium chloride because it breaks into 3 ions. See, 1 and then 2 more. So 1 calcium, 2 chlorines. All right, now we're going to move on to example 12.12, and you can stop and breathe for a moment if you want to. Example 12.12 on page 317. Now you will need to be able to do all these example problems. There's a quiz coming up on Thursday, so you need to make sure you can do these for the quiz. All right, compare the freezing points of, now we're going to do 3 of them. We're going to have a 3 molal solution of sugar, which is, C6H12O6. We're going to have a 3 molal solution of sodium chloride, and we're going to have a 3 molal solution of calcium chloride. And we're going to compare the freezing points. Okay, so for all of them, they're going to use the same formula. Delta T sub F, negative, I K sub F M. They're going to use each one of them. All right, now we're going to go in and fill it all in. What is the I for sugar? C6H12O6. This is a covalent molecule. It breaks into just molecules, pieces, not individual ions. I is 1. What's the I for sodium chloride? 2 pieces. I is 2. What's the I for calcium chloride? 3 pieces. I is 3, because there's 2 chlorines and 1 calcium. So we're going to do 1 times the K sub F for water, which the K sub F for water is 1.86 degrees C per molal. And they gave me the molality each time, so I don't have to figure that out. Times 3. So really the only thing that's changing in all these guys is the I value. So this is 2 times 1.86 degrees C per molal. And this one is 3 times 1.86 degrees C per molal. And the same molality. All right, we have to put in all these guys into our calculators to see what the delta T sub F. Remember that we're also going to need to multiply the final answer by a negative sign, so that we end up saying that delta T sub F is negative something for each one of these guys. All right, let's do the first one. 1.86 times 3. All right, the first one is 5.58, or a negative 5.58. Because the m's cancel, it's degrees Celsius. Second one, move my calculator over, is 2 times this same quantity. I'll just do it piecemeal. 2 times 1.86 times 3. So 11.16. And there's 3 significant figures, so 11.2. Because the m's cancel. And the third one is 3 times this times the stuff. So 3 times 1.86 times 3, or 16.74. 3 significant figures because of here, 3 significant figures. So 16.7. So, which one of them lowers the freezing point the most? The guy who has the greater particle count, negative 16.7 degrees. The freezing point would go down negative 16.7 degrees. And since we're dealing with water, if I wanted to know what the freezing point rather was, I would put in the change in it. This number right here would go directly into here. Negative 5.58 equals, what's the new one? Minus the original freezing point of water, which is 0. Well, so since it's 0, just add 0 to both sides. So the new freezing point is actually the negative 5.58 degrees Celsius. 58. It won't be that for other solvents because the freezing point of other solvents will not be 0. So over here, the new freezing point is 11.2, negative 11.2. The new freezing point is 16.7. So how is this applicable to real life? When you can put salt on the roads to lower the freezing point so that the roads become liquid water and drain off rather than becoming ice. And you can Google what kind of salt do they use on roads? Google salt used on icy roads and find out what the formula is. Well, we did that in class before, but you can do that right now. And if you do that, you'll be able to see that a lot of it is sodium chloride, some of it is calcium chloride. And then they also have some other things inside the salt to try to keep it from clumping up. And in the south, sodium chloride will be just fine, because I don't think we're going to get down to negative 11.2 degrees Celsius. But we could. And the lower the freezing point, the better off we'll be. So anyway, that's how it's used. Next is osmotic pressure. You just basically, you cover this in biology. Osmotic pressure is a process in which a solvent moves across a semi-permeable membrane, like a cell membrane. Osmotic pressure of a solution is the amount of pressure required to prevent osmosis from occurring. So how much pressure will hold it all in. The more solute particles there are in the solution, the higher the osmotic pressure will be. Okay, we're going to move on to colloids in another video. Good luck with your homework.